Dear students, in this lecture, we are going to see the different types of impedance matching techniques that we use in a transmission line. If we want to match the load impedance with that of the source impedance, then we can do it in two different ways. The first one is using short length transmission lines. That is, we can make use of a short piece of a transmission line of certain length between the load and the source to perform this impedance matching. The different types under this are, we can either make use of a line of length lambda by 8 or lambda by 4, or you can either use lambda by 2, which is named as 8-wave line, quarter wave transformer and half wave line. In the previous video, we have seen what is quarter wave transformer and how impedance matching is done using quarter wave transformer. Now, in this video, we are going to view how this H-wave line and half-wave line works. In addition to this short-length transmission lines to provide impedance matching, we can also make use of stubs. There are two types of stubs that performs impedance matching between a load and the source. It can be named as single stub matching and double stub matching. Now, in this video, we are going to see the explanation of half-wave line as well as 8-wave line. H-wave line. As I told you, as the name implies, the length of the short section of a transmission line that we insert between the source and the load to provide impedance matching will be equal to lambda by 8. That is why we name it as 8-wave line. It is clearly shown in this picture. This part represents the source. We have a source voltage, source impedance, and this part represents the load. Now, in between the load and the source, we have inserted a short length of a transmission line, which is shown in this dotted portion. And the length of this inserted line is made equal to lambda by 8. Now, we have to find what is the impedance of this lambda by 8 line. This is what we are going to find out. In general, the input impedance of a dissipation-less transmission line is given by this expression. ZS is equal to R0 into ZR plus JR0 tan beta S divided by R0 plus JZR tan beta S. Here, beta is 2 pi by lambda and S is the length of the transmission line. That is the distance measured from the receiving end. So, as we know, beta is 2 pi by lambda. And here in this case, the length of the transmission line that is inserted between the load and the source is lambda by 8. So, we can find what is beta S. Beta S is 2 pi by lambda into lambda by 8. Lambda will be getting cancelled and you will be getting only this pi by 4. So, beta S can be taken as pi by 4. Now, let us find the input impedance of this, which is given by ZS is equal to R0 into ZR plus JR0 tan beta S. Beta S we have determined it as pi by 4 divided by R0 plus JZR tan pi by 4 again. In an 8-wave line, this is given as pi by 4. Beta S is given as pi by 4. Now, we all know that tan pi by 4, which is 45 degree, value is 1. So, this gets simplified as ZS is equal to R0 into ZR plus JR0 divided by R0 plus JZR. This is the impedance of the 8-wave line that we insert between the source and the load. Now, if this line, the line that we use, if it is terminated with a pure resistance Z, that is RR. In the previous expression, if we take ZR as RR, then the same expression can be written as ZS is equal to R0 into RR plus JR0 divided by R0 plus JRR. If the value of magnitude of ZS is determined in the above expression, that is, if we determine magnitude ZS, we will get magnitude of ZS is equal to R0 into root of RR square plus R0 square divided by root of R0 square plus RR square. So now the numerator and the denominator are same, so it can be cancelled and you will get the magnitude of ZS as R0. So we can say the 8-wave line is used to transform any resistance to an impedance with magnitude equal to R0 of the line. Clear? The next is half-wave line. This half-wave piece of a transmission line can also be inserted between the source and the load in order to provide impedance matching. So here again there will be a voltage source. You have a source impedance ZS and we will be inserting a piece of a transmission line between the source and the load. This is the load. We can take it as ZR, load impedance. Now this short piece that we have inserted between the load and the source is of length lambda by 2. That is why it is named as half-wave line. So we are inserting a transmission line, a piece of a transmission line of length lambda by 2 between the load and the source now. Again, in this case also, we have to find what is the input impedance of this half-wave line that we have inserted between the source and the load. Okay. Now, from this expression for ZS, we can have ZS is equal to R0 into this value. ZR plus JR0 tan beta S divided by R0 plus JZR tan beta S. Now, we are supposed to find what is beta S. We know that beta is 2 pi by lambda and S in this case is the distance from the receiving end, which is nothing but lambda by 2. So here we are going to get 2 gets cancelled. Beta S is going to be pi. Beta S value is going to be pi. Now if you substitute beta S as pi here, you will get ZS is equal to R0 into ZR plus JR0 tan pi divided by R0 plus JZR tan pi. What is the value of tan pi? Tan pi is 0 radians. So this second term will be 0. This will be 0. So we'll get ZS is equal to R0 into ZR divided by R0. This gets cancelled and we are left with ZS is equal to ZR in case of a half-wave transmission line. So in half-wave line, ZS will be equal to ZR. So you can say that half-wave line repeats the input impedance of a half-wave line will be same as that of the load impedance, right? So repeats its terminating impedance. And this will function as a one-to-one transformer. Hope you understood these two topics. Thank you.